Hello, this is Dr. Flight, and this is going to be a video discussion on the results that you identify from a logistical regression in SPSS, and just some of the things you want to look for once you run the actual regression with the Logit model. So just recall that the Logit model will actually have two different stages that are relevant here. So first, the model that'll be created will be this model here, which is G of X. So it's the G of X model that we'll use, and these betas that are identified here are actually the coefficients that are specified from the output, which we then place into a formula here, which will help us predict whether individuals in a one group or another in our Logit model in the dichotomous variable, that is the dependent variable. So we'll actually use this function and the value that's created here, which will be then placed into our probability function to create the probabilities which will place groups, an individual in one group or another. So that's the steps that we're doing. Remember, there's the odds that are happening that are being created from this. So again, we take the g of x and we input it in here, which is the same as up here. So this pi sub x will ultimately become a probability. So we're going to walk through that actually in the output file. But as we go forward and we think about what the output's all about, we're going to look at goodness of fit and how well the model is estimated. And as we do that, one decision that you'll have early on is to decide which way you want the independent variables to be entered into the actual model. So this is just like a multivariate regression where you have a choice of entering all your variables at once or having them sequentially entered by their level of importance, if you will. So an enter method would take all of your independent variables, put them into the model simultaneously, and then you would need to determine which ones are the most important, which ones to keep, and so forth. Forward and backward stepwise regressions enter the variables one by one, depending on their most or least level of importance. So a lot of times with regressions, if you have a lot of independent variables or you are exploring the variables which you don't know which ones are going to be the most important, sometimes you'll indeed do that. The walled approach or walled measure will be a test or a statistic that's used to enter variables. If that's chosen, you may do that too. So you can have a forward walled entry, for instance, or a backward walled entry. And those are popular. So in SPSS, when you look at it, you have the entry method that you can choose, and this drop-down box here will allow you to do that. And your box may look a little bit different depending on the version of SPSS. Don't let that throw you off. They will all have this method area available for you. So once you identify that method, then you go ahead and go into options, and you can go into save as well if you want to save group membership and the probability of group membership. But you can go into options here and check the appropriate boxes. A lot of folks like to have the confidence intervals checked. A lot of people should certainly look to do the Hosmer Lemon Show goodness of fit box there. If you're concerned about outliers, you may also want to check this outliers case-wise listing for residuals box as well. One last thing I want to note here on this page is the specified cutoff point of 0.5. We'll come back and talk about that a little bit. The norm is to use 0.5. You could change that if you felt like you needed a different cutoff point. But again, I will look at that here in just a second to indicate what you do. So in SPSS, if you go to the Analyze tab, then go to Regression, then Binary Logistic, you'll come up with this dialog box and you'll have these options available to you. So getting into some of the data, once you specify your model, and by entering your variables, your dependent variable, of course, is a dichotomous 1 or 0 variable. The rest of the variate, the independent variables, could be metric or non-metric. So there's a lot of flexibility there in terms of what you may want to do. But you specify your model, and then you run your model. And you're going to get a series of boxes and tables so that you can help identify, the best fitting model and the independent variables that work best for you. So one of the and these are in different order. These are not all in sequential order that you'll see in your output. So these are the boxes that you'll want to find, though. One of which will be the model summary, and this is like in regression where you have a summary box that gives you the R-squared and adjusted R-squared, and so this would be like your model fit here as well. In this particular case, the R-squared that you look for is the Nagelkirch R-squared, which is 0.214, which would be acceptable. We would like it to be higher, obviously. The higher the better. So if we could find other variables, independent variables that would meet that criteria better or raise that, then we certainly would like to do that. So preferred reporting variable here, or R-squared, would be the Nagelkirch R-square in this particular type of regression. The minus 2 LL is actually, as it states here, similar to the residual sum of squares. As you have a better fitting model, this will go down. Now, in this particular approach, we used a stepwise regression. It was a forward walled, and there were 2 steps that were created. So remember, in a stepwise regression, you have you'll have a step, and then you'll either add variables or delete variables from the step. And then in the next step, you'll run a second model. SPSS will run a second model. And then assuming the fit's better, it will run a third and a fourth and a fifth, depending on how many times it needs to, either adding or deleting variables. This particular output shows that there were 2 steps taken and that the best fitting model, which would be the second one, emerged, and then a third or a fourth model that could have been created would have successively done better, but it wasn't possible. So this will be the best that we can do. This number 120, again, the further it goes down, the better to 1. If it goes down, this R-squared will go up. So there's a relationship there, but this would be the first thing, one of the first things to look at, not certainly the only thing, but there are lots of different ways we can tell whether the model is going to fit or not, and this is one good indication that we would report. Another indication is the Hosmer Lemon Show test, and this is basically a test between the fitted model, which again is step 2 here, the final fitted model, and it compares the fitted model to what we call a base model or base level model. And we'll look at that in a second, where we look at the base level model and the predictive capability of it. And then we look at the predicted model, and we look at the probability of success for the predicted model, and we compare those two. If there's a significant difference between the base model, which would have no independent variables in it, and the new model, which includes independent variables, if there's a significant difference there, then this will be above 0.05. So this is a reverse indicator of significance. So we want something above 0.05 in this case to indicate that this model is significantly different than another. So this is another item that you report. You can report this this chi-square with the degrees of freedom, with the significance, and indicate that it's above 0.05 to suggest that the model that you've created significantly predicts group membership better than a baseline model. And here's a little bit more on this idea. When you run the model, the output will provide what's called this base model classification table. And in essence, what it's telling you is that if I took all of my respondents, and in this case there's 104, if I took all of my respondents and I grouped them all as, in this case, either A or B, if I grouped them all in one of my classes, then I would have a 61.5% success rate. Okay, so this 61.5% is the base level that if I did nothing, if I did not have any independent variables at all to help me predict this model, I could do a 61%. I would be right 61% of the time, basically, in my assignment. And that I would do by just putting everybody in the top group here, and that's how that would work. Now, what we want to do is we want to look at this 61% and we want to compare it to the predictive model that we created with our independent variables. So we're going to look at this base model and we're going to compare it to the predicted model, and you're going to see that the predicted model predicted accurately 75% of the cases. So in other words, 75% of the cases were properly placed into either group 1 or group 2, and that is a clear improvement over the baseline model, and that's why the Hosmer case Lenshow test was significant at such a high level. And in fact, if you look at the change in predictive capability, the new model that we created predicts membership properly 21.9% better than the base model. So that's a great improvement over what we had, and is an indication again that this model will, is at least sufficient in better predicting group membership than if we had no model at all. So moving forward, we have another box. So this is the third box or table that we can look at. This is a really important table because it indicates and shows the level of strength that our variables have. Now, again, step 2 is the model, the final model that was produced. We originally started with 6 variables. Only 2 of them ended up being significant, and they only show 2 here because we used that stepwise approach. So if we had used the enter method, then we'd have all 6 variables here, and we'd have a coefficient for all 6 plus the constant, and we would have a significance level for all 6. Now, it's the case that there's only 2 variables here that are significant, so they're the only 2 that show up. The other ones that are not significant, of course, dropped out of the model and aren't reported at all. So if you want to look at those other variables, use the enter method, and you'll get all of the results from the entered method that's there. And your R square may go up a little bit because you're adding variables and so forth. So let's look at this a little bit more and talk about how these are used to actually predict group membership, because this will actually be fairly important. So let's remember that we have a function called g of x, and back here, if you look at this table right here, you'll remember this from a few slides ago. G of x is a function of our variate. So we calculate g of x for each respondent based on this variate. Now this is b sub o, that's our constant, plus b1, x1, b2, x2, and so forth. Here in this model, we only have x1 and x2, so we only have b1 and b2, and the constant. So we actually just have this front end of this variate because we only have two variables here, case and test 3, and then our constant. And you'll notice that the g sub x variate or function here for each individual respondent is calculated above. So we have negative 6.874 for the constant plus 4.128, which is multiplied by the case score for each respondent plus 5.079 times each respondent's test 3 score. And that will give us our G sub X calculation for our analysis. So that is the first thing to look at and to think about here as we continue to look at this table. You'll notice that there is a value associated with this. So the Wald test, which takes the which actually takes the beta score, and let me just double check here, or hold on. Yeah, sorry for that delay. It takes the beta, divides it by the sum of squares, sum of the error here, and then that's squared, and that actually produces the Wald statistic, which is then tested with 1 degree of freedom, and that produces the significance level here. So that's important. Oh, actually, that's right here. I don't know why I hesitated. The actual Wald statistic is calculated there, and that's what's provided. So this you can think of as, in a regression, we have a t-test, which tests whether the beta is significantly different from 0. Here, because of the calculations that are used, and we're using this Wald estimation or Wald statistic, this is the test that we use. Again, if you're using the enter method, you look at these to identify which variables would be significant in helping us explain group membership. Another aspect here that we want to look at, or we want to think about, is how we use G sub x to create a probability in which we'll place our actual respondent. So remember, this is a two-function, two-step process that happens. A G sub x function's created, then that function is used to create probabilities in which we'll place our respondents. Now, remember that cutoff point of 0.5? When we create the probability, anybody who scores above a 0.5 in probability will be in the first group, and anybody below will be in the second group. So that's how that is created. So this G sub x is actually the logit that's created, and then the odds are created after that. So the first model then will be the logit, and then we have odds that are created. So so that's what we're looking at here. A ton of information here. In another slide or two, we'll actually look at the exponential here of B, in just a couple seconds. But we're going to talk about this a little bit more, and let me just illustrate using Excel how this G sub x is created, and then how we use it as a and we turn it into a probability, which will then help us to determine group membership. So here we're looking at a Excel sheet with our raw data, and we're looking at the group identifications, and I just grabbed some data from the data file. So this is our DV here, the group that they're in, and then we have our IVs here. And this is the G sub x function, which we just saw on the last slide. And basically what we're doing is we've got our constant, which is the negative 6.874, and then we have our 4.125, which is multiplied by the case number, and then we add to that 5.879 times our test 3 score. So this G2 is the test 3 score, this C2 is the case score, and so this variate predicts or creates the function G of x for each respondent. Now, what we do at that point is take the G sub x and we put it into our P sub x, or our probability function that was outlined before. So we take the exponent, this is the log exponent. So the exponent J2, which is going to be this G sub x, divided by 1 plus the exponent of J2 again, so 1 plus the exponent of G sub x below. Again, so this is just a division of this function of G sub x divided by 1 minus G sub x, so in the exponential formation or calculation thereof. That function, so this is actually the Excel formula. This is the Excel formulas to create these columns. Now what these are, and interestingly enough, these P's are percentages. These will fall between 0 and 1. So it's a percentage likelihood that we're really creating here. Now the very last step is to apply our cutoff. So remember, our cutoff was 0.5. Anything above 0.5 will be classified a 1. Anything below 0.5 will be classified a 0. That's the cutoff that we use. So this third column is simply an if statement. If the P sub x is greater than 0.5, it'll be a 1, and if not, it'll be a 0. So again, we're just classifying now each respondent as to whether, it's above or below a 0.5 based on this probability that was created. Okay, so 2 steps. We create the function, G of x function, and then we use that to create a probability, and then that probability determines which group we're going to place the respondent in. Now, the thing we can also do here, which is interesting, is we can look and see, this is the prediction, and then if we go way over here, this is the actual. So we can look and see, like, this first case was predicted correctly, but the second case was not. The second case predicted a 1 and it was actually a 0. Third case was predicted correctly. Fourth case was correct. Fifth case over here was incorrect. It predicted a 0 and we actually had a 1. Okay, so we can actually go through here and we can look at the success rate between actual predictions and then actual group placements, and then that will help us determine what we're doing. And again, we already saw that this predictive model should predict accuracy at 75%. So 75% of the time we're right. This model is correct in showing group identification. All right, so that's how that looks. Now, walking back to this table one more time, we can see how these two variables, case and test 3, are significant, and they help predict group 1 membership, and they do again at a 75% rate in which they occur. What we also look at now, and we didn't talk about it in depth earlier, is the exponential b. So if we take the exponential of this b, we get this exaggerated number, the 67.9 and the 160.6. This is actually very interpretable. So what this means, this is the strength or the power or the magnification, if you will, that these variables play in placing an individual in the first group. So the way we interpret this is a unit of increase, or 1 unit increase in the case score helps increase the likelihood of placement in group 1 by 67 times. So in other words, if a student does better in case 1, they have 67 times the likelihood of being placed in the top group than otherwise. And in this case, these are like high achieving students to low achieving students. So if you do well on case 1, you have a 67.9% or times, you're 67.9 times more likely to be classified in group 1 than in group 0. Now test 3 is even more important though. If you do well on test 3, it's 160 times likely that you're going to be classified in group 1 than in group 0. So again, this is a very powerful reporting tool to indicate what's going on. Now imagine if we were trying to predict customer purchases, for instance, and we realized that if we have good customer service, then that's a good indicator that a customer will buy from us. So let's just apply this. Let's say customer service was here and we had a 67 here. It would mean that with each increase in customer service, the customer is 67 times more likely to buy than if we did not have that increase in customer service. Okay, so that's actually a really powerful application to interpret how strong these independent variables can be and what their meaning is in terms of focusing on growth. So if I was a student and I saw this data, then it means that I would have roughly 2.5 times as much impact if I do well on test 3 than if I do well on my cases. So basically what's going to happen is I'm going to really study hard for test 3 because I know that's a good predictor that I'm going to do well in the course. Okay, so there are several boxes here, or tables that we look at in the output file. And as you walk through examples, play around and look at these and work on your interpretation of these data and what they mean. Also, test doing the entry method through either enter or a stepwise entry method, either forwards or backwards maybe, and just see what the differences are in terms of your analysis, and try to understand goodness of fit and whether the model is strongly predicting group membership above and beyond the base model, and then the degree to which it is. All right, so that is an analysis of the output that emerges from Logit. Thank you for listening. Please feel free to touch base if you have any questions. Thanks.